where you have a glucose removed and another one put on. It's kind of a change the tires on your car when they're all worn out. And if that makes your car drivable, fine. But if it doesn't, then you just got to keep fixing things till you get it right. So what usually is given as the figure is 3 times. You get 3 chances to go around here and get your act together. If you do not follow correctly or whatever, you still flunk the test, you will actually be sent out from the ER and you're going to be destroyed. If, however, you're okay, like 3 times you're all okay, then you're allowed to go to the Golgi. So what happens if you get kicked out of the ER? When you get kicked out of the ER, remember, now we're back down on the bottom. There's ER lumen. I wish you could keep the orientation the same on adjacent slides, but here's the ER lumen. Here's the chaperone that's been looking at you saying, well, you just still couldn't get it together for 3 times, so you're leaving. You actually end up having that chaperone take you up to the same translocator core, that protein through which you entered, and it will boot you out into the cytoplasm. So this is the cytosol up here. In the cytosol, you are going to be ubiquitinated. Remember that story when you add on the ubiquitin? So you have this one ubiquitin flag that's going to say, take me to the proteasome, and chew me up, except we know that if you add a second one onto the first flag, this big long flag, you are going to be more recognizable, as you could say. So you're,
I'm sorry, is there some sort of sequence that the chaperone is just going to recognize, or is it something else?
It's really a shape type thing.
It's a shape?
Yeah, it's a shape type thing. It's a very specific shape that final confirmation has to have. And I'm making it sound a little more magical than it really is. I'm just going to leave it at that. If that's okay with you.
Yeah. So chaperones are going to work more quality rather than.
Yeah. They're not going to be actually looking at the glucose. It's an overall thing. Because, they can't go in there and read the amino acid sequence or anything. So everything is about charge, density, shape, and so forth. Okay, so there you are, eaten up in the proteasome, and then your individual amino acids are spit out. And guess what? You can turn right around and use those in translation to make a new protein. And maybe have better luck in your second life than your first.
So is that an asparagine glycanase that's going to take the sugar back off before it goes to the proteasome?
Yeah,
Is that what that's supposed to
yeah,
be?
I was trying to avoid that. It's a very good question. That didn't come out wrong. It sounded terrible. I didn't mean it the way it sounded. Yeah, this is part of the checking mechanism here. Yeah. Very good question. I wish I had time to go into it because it's really cool. I'm just going to have to pick and choose in this last lecture, and I apologize. Okay, so anyway, there is one more phenomenon that can happen in the endoplasmic reticulum, and that is that you can be linked to an anchor. You as a protein can be linked to an anchor. This anchor is glycosyl, phosphatidyl, and inositol. Now, what that means is that you, when you get in, and I can't even begin to tell you the mechanism here for lack of time, so I'm just going to have to ask you to trust that it is a controlled thing. But in the ER membrane, facing inside here, but also extracellular, is this GPI anchor, is what we call it. You have the full spelling up there, and you should know the full spelling of it. All this is phosphatidyl and inositol. Remember one of your phospholipids? But it has a glycosyl group on it, so let's look at it on the slide here. So this is the structure right here that is sitting in the membrane not reaching into the cytosol, that's incorrect. No. I'm going too fast. Take that off. It's strictly membrane bound and then intra-ER. Apologize for that. Okay, so it's sitting there, and what's going to happen is this. If you are translated and you are still membrane bound in the ER, in other words, you were not completely shoved in there and let go inside the ER lumen, there will be an enzyme that will recognize some sequence here and will cut you off from your transmembrane segment and then turn right around and attach you to this pre-made GPI anchor. And this is a fascinating story, and I just hate we don't have time to go there. I feel very badly, but what's going to happen is that eventually, on down the road, you are sitting inside the ER as a protein. You have this attachment to your membrane, and the glycosyl groups are there and so forth. You're going to be going to the Golgi. You'll leave the Golgi in the same orientation. And then you'll go up the plasma membrane surface, open up, and what you'll end up with is this structure right here, hanging out there in the breeze, outside the cell. And so you just have to accept that that's a very important signaling molecule. It's like a flag on the surface of the cell. So GPI anchor occurs in the Golgi. In the ER, in the smooth portion of the ER, we also have fatty acid synthesis, lipid synthesis. I am not going to hold you responsible for this. We just don't have time. Just recognize simply that inside the ER lumen, we are going to be putting our lipids together. What is pitifully condensed, but that's all we can do. You concentrate on protein synthesis in the rough ER. Simply know that smooth ER is lipid synthesis, but you certainly can read it in your book right around 1257 if you're interested, but I won't be testing you on it. Okay, this is simply showing you something that can occur once you have made all of these lipids back here. You didn't get to see. You're going to have different head groups facing outside versus inside. In one case, it's going to be inside the ER versus the cytosol, which is outside the ER. Over here, we're talking about the plasma membranes that are inside the cytosol versus outside cytosol. So that's the outside world here. So notice the designations here, ER membrane and plasma membrane. So what happens is we make these lipids, we stick them in the membrane, and there we rearrange them. It's a whole big story here. We rearrange them because our membrane is asymmetrical. We do not always have the same phospholipid facing out as we have facing in, and it's due to this action. All I want you to know is that there are two enzymes that are responsible for creating this asymmetry of phospholipids. One works in the ER, one works in the cell itself, inside the cell membrane. In the ER, it is called a scramblase. That is the enzyme. It scrambles the phospholipids around. Scramblases require ATP. If you're keeping that list, like I told you, it'd be real wise to do, and you could add that. So that's strictly ER. Very parallel to that is occurring in the plasma membrane is a flipase. A flipase is doing the very same thing.
Where is it taking place at?
This is in the plasma membrane, the cell membrane. So you have the cytosol here. Here's your nucleus and all that. Here's your cytosol. So you have one set of phospholipids facing that way, one that way. 2 leaflets of the membrane, that is where your flippers works. Whereas your scramblase works over here in this one, in the ER.
They both need ATP or?
They both use ATP. There's one exception to that, but we're just gonna take the general rule.
But it's in the plasma membrane of the cell in the ER, right?
We need to back up here. I probably went so fast I lost it. We have 2 different membranes we're looking at. One membrane is, no, it's okay. One membrane is the cell membrane, okay, that encloses the whole cell. And that is done by flippase. So it takes this, it just creates the asymmetry in the plasma membrane. The other one, the scramblase, works in the ER membrane. So it's along that membrane, which looks just like that, with the phospholipid fixing one way and the phospholipid fixing the other way. And it does its trick there.
So, CellPhys is facing inside the ER or out into the cytosol as well?
Oh, you want to know where the enzyme is? Is that what you're asking me? Okay, the flippase, the flippase is here. It's in the cytosol.
Yes.
Yeah, and over here, so it's out here in the cytosol, in here, I have to have larger ER. Do the bigger ER. This is an ER of a kid whose mom gave him phenobarbital. Bigger? This is smooth ER, by the way. And this is also lipid, and here is where your scramblase is inside the ER lipid. Okay? Very good question. Because that's where you're doing the lipid synthesis. Without that earlier story, I can see why you were confused. Okay? All right, moving right along here. We're going to go to the Golgi now. Now this gets kind of interesting, because what happens is that if you're a protein, let me back up. If you're a protein and you are, let's take it a protein number. Sorry, I want one that's losing the slides. There, that one, slide 10. If this is you as a protein in the ER limit, you are either going to be designed to stay there the rest of your life, or you're going to be designed so that you can move on to the Golgi. Those are your only 2 choices. If you are to stay in the ER forever and ever and ever, this is very important and you must know it. If you are to stay there and not go on to the Golgi, you will have a sequence at your carboxy terminus that looks like this. It's referred to as the K-del sequence. These are the 1-letter codons for 4 amino acids. They are not just found anywhere in the protein. They're only the last 4 at the C terminus. So if you put K-del down on the test, you get it all wrong. It has to be at the carboxy terminus. Okay, I'm never good with this. I know that's lysine. I think that's aspartate. Help. If I know what it is. Is that glutamate?
It's an acid, glutamic acid,
Glutamate?
or is it?
Glutamic acid? Well, we don't know who he is.
Yeah, it's glut, yeah. So
Wait a minute, that's lysine. Or is that lysine?
License?
I'm not gonna ask you the amino acids, you can look them up, but just remember K-del. I don't know my 1 letters, inexcusable, but I don't. So anyway, these 4 amino acids, K, D, E, L, at the carboxy terminus are called an ER retention signal. That means you are supposed to live there forever and ever and ever. ER retention signal. That means that you are an ER resident protein.